All right, so this is AtwoodsMachine right here. We have a 200-gram mass on the ground here, and there's a 200-gram mass here. I've measured the height from the ground to the bottom of this 200-gram mass, and that is 1.662 meters. And so I'm going to add a 20-gram mass to it so it will fall. I don't have it attached already because I don't want it to fall yet. All right, so in order to time it, I've got my phone. It unfortunately only goes out to 1/10 of a second. So, you know, it is what it is. So we'll put that on there. And I'm going to attach my 20-gram mass up here. All right, so right now my foot is keeping that pin down, and so I'm going to start as soon as I take my foot off in 3, 2, 1, go. All right, I stopped when I got down to the bottom. It was 2.8 seconds. Let's do it 2 more times just in case there was some other issue here. And one of the issues is that, wow, that really bounced. All right, so I only did it once, and I realized that as I was trying to set it back up again, the distance would be very difficult to establish the second time because it became, the string came untangled, and so it no longer became worth the effort. So we're going to stick with the 2.8 seconds. And so we're going to, first off, we need to figure out what is the final speed. In order to find the final speed, it's just the magnitude of the final velocity because it's, well, it's instantaneous, and also it's only traveling in one direction. So it becomes a classic chapter 2 problem. So the distance it's going to travel is 1.662 meters. I'm assuming down is positive. So the displacement is 1.662 meters down. The initial velocity is 0 because I started it at rest. Acceleration, I don't know. Final velocity, I'm trying to find. And the time was 2.8 seconds. So yeah. Now, in order to find it, I need to exploit the definition of average velocity and how we can also, the alternate way of finding average velocity if acceleration is constant. Average velocity is always displacement over time, but if acceleration is constant, it's also v, just the average of the initial and final velocities. So therefore, I can find my final velocity just by, well, my displacement is 1.662 meters over 2.8 seconds. That is equal to my VI, which is 0, plus VF over 2. In other words, my final velocity is just going to be twice this right here, twice my average. And so my final velocity is 1.662 divided by 2.8 times 2, and we end up with 1.187143 meters per second. So that's my average velocity, that's my final velocity, and so my final speed will just be the absolute value of that. So now we're going to find out if this relationship holds true. So mass 2 was 0.220 kilograms. Mass 1 was 0.200 kilograms. I'm trusting that what's printed on there is close enough for what we're doing. So mass 2 minus mass 1, the difference is 20 grams or 0.02 kilograms, so this is 0.02 times 9.8 times the height of 1.662. And the question, is that equal to 1/2 times the total mass, which is 0.420, times the speed squared, 1.187143 squared. And so now let's find out using the handy dandy calculator here. So I take that value squared times 0.5 times 0.42. And on the right hand side, I get 0.296 joules. On the left hand side, 0.02 times 9.8 times 1.662, and I get 0.326 joules. Now right off the bat, you might go, wait a second, math class tells us that's not the same thing, but it's physics. We're trying to find out what is the relationship. Because they're both found experimentally, we can find a percent difference between the two. So the percent difference is the difference between the two, so 0.326 minus 0.296 divided by the average of the two. Because we don't know which one is actually the correct answer, we have to do a divide by an average. So we assume that the average value is correct. So 0.326 plus 0.296. So on top here, doing the fancy math here, this is 0.03, and on the bottom, should be 0.311. Yeah. So 0.03 divided by 0.311. So 9.6% off. We're under 10%, which for the most part, there's some satisfaction in physics when the percent difference is under 10%. So I'm feeling pretty good about that. So anyway, this is AtwoodsMachine. I might or might not have you do the lab on this one. I would give you the times and the distances. It's not particularly exciting, it's just some number crunching. However, it is sort of trying to reinforce this idea that the total work done on a system is equal to the change in kinetic energy. And with that, I'm going to stop it, and I think that's a wrap.